Let's compute the relative extrema of a function of two variables. In Calculus 1, you did this type of exercise quite frequently. And so what we want to do is utilize the same techniques to work with a function of two variables. So we may be asked to compute all relative extrema and saddle points of a function of two variables. In this case, we have fxy equals 2xy minus 1/2 x to the fourth minus 1/2 y to the fourth plus 8. Now, in this case, we have no restrictions on xy, so we're only going to be looking for relative extrema, but you can see in this particular case that since we've got these dominating terms with negative coefficients, that further analysis would yield that our relative extrema that were classified as maxima would be absolute. So again, just remember, this is just like the technique from Calculus 1. We look for critical points and then we analyze them. So in order to do this, we look at the partial derivatives of f with respect to x and y. So fx and fy, this will give us for the x partial 2y. And then of course, 4 times the negative 1/2 is a negative 2x cubed. Likewise, for the y partial, we get 2x minus 2y cubed. Now, just like in Cal 1, we're looking for horizontal tangent planes. So we have a system that we must solve. So this reminds us of our college algebra days. So I guess, again, what we see here is that the 2's absorb, and we get y equals x cubed. And for the second line or the second equation, we get x equals y cubed. Now, at this point, you can use any method you like, but just remember the method of substitution turns out to be very useful. So now if we notice x equals y cubed, but y is x cubed. So we can just make a substitution. X is equal to x cubed, which is x to the 9th. Now, at this point, what we can do is just transpose and factor. So we have x to the 9th minus x, and just move through with a series of factoring to look for real solutions. So we have x to the 8th minus 1. And then, of course, we have a difference of 2 squares. So this gives us x times x to the 4th minus 1 times x to the 4th plus 1. Of course, this only has imaginary solutions, so we'll just continue to factor the difference of squares in this term. So this will give us x squared minus 1 times x squared plus 1 times x to the 4th plus 1. And then the last difference of squares is right here. Go ahead and factor. So we're doing a real factorization. X minus 1, x plus 1, and then the remaining 2 factors that only have imaginary zeros. Again, these are not unimportant. It's just that we're doing calculus of real variables, so they're not important to us for this problem. So now, of course, this is equal to 0 from our original equation here, or system of equations. So now we can use zero product. So this will give us what? X equals 0, or x equals 1, or x equals -1. Now, of course, we have from the system this connection, so we can clearly figure out y from the values of x. So we get a 0, 0, and then when x is 1, 1, 1. And then when x is -1, -1, -1. So this gives us what we need in our analysis. These are called critical points. So we're looking for our horizontal tangent planes. We know where they are. And now what we want to do is analyze these, classify them. So remember, for the second partials test, we need fxx, fyy, and fxy. Now, you could do fyx. We remember earlier in the chapter, we had Clairaut's theorem, which was the equality of mixed partials. The proof probably looked fairly daunting, but it actually utilizes the directional derivative that you just studied. And so now, if you go back and look at that proof, it's a very straightforward application of the directional derivative. And so it'll make a whole lot more sense when you see that in the context of the material that you just studied. So now fxx will give us a negative 6x squared, just taking the derivative here, and now taking the derivative with respect to y. Again, we just get negative 6y squared. And then, of course, the y partial of fx will just give us a 2. So to make the expression d, we have what? fxx, fyy in product minus the square of the mixed partial. That comes from our second partials test. So the product here will clearly be 36x squared y squared. And then we have to square the mixed partial, which gives us a 4. So this gives us the expression that we need to evaluate. And also, just to remind you, we also need the value of the second order partial with respect to x. So when we do the analysis, it might be good just to write a column for a critical point, then a column for the second partial with respect to x. And what you can do is just go ahead and write it down so it's easy to evaluate. And then we have d, so we'll just fill it in with what we computed here, 36x squared, y squared minus 4. And then we want the class. What is the classification? I'll just put class for short. And then the value, that is, what's the value of the function? And let me write that equation down, 2xy minus 1/2 x to the 4th minus 1/2 y to the 4th plus an 8. And then, of course, we'll just fill these in with the 3 critical points that we have. So we've got 0, 0. We have 1, 1, and -1, -1. So we'll have a column here, another column, and then here for the last column. So, and of course, now when we use 0 here, we just get fxx is 0. And then for d, we have 0 minus 4, which is -4. So this is less than 0. So we know from the second partials when the d is negative, irrespective of the second partial with respect to x, we get what we call a saddle point. So I'll just put saddle. And then what's the value of the function? Well, that's easy. We just get a bunch of zeros here and an 8. So this is 8 very clearly. And now if you like, you can just write the order triple, 0, 0, 8. Now this is not specifying the value of the function. Clearly it's this, but we see that in the final coordinate. Now for 1, 1, we just have what? -6, which is less than 0. And then for d, we have a 36 minus a 4, which is clearly positive. Now from the second partials, that gives us a relative max, just the same as you would have in calculus 1. Now when we evaluate, what do we get? 2 minus 1/2 minus 1/2 plus an 8. So that's a 1 plus an 8, which is a 9. And then we can just write the order triple, 1, 1, 9. And then for the last critical point, again, we have the same value, -6, just substituting here. And then d again is not changed. I'll just go ahead and put d equals. I don't know that I have to do that. So we have 36 minus 4, which again is positive. So we have the positive d, the negative second partial with respect to x. The derivative test gives us a relative max. And then we get the same value. I'll write this down. Minus 1/2 minus 1/2 plus 8. And that gives us a 9. So now the ordered triple is -1, -1, 9. Now notice in this particular case, we did not get any relative minima, but just as a summary here, remember when we use the second partials test, if the second partial with respect to x is positive and d is positive, this implies the relative min, which we didn't get. And then we got two relative max. That's fxx is less than 0. The d is positive. This implies the relative maximum. Now, the case that's actually important for the saddle is when d is less than 0. This implies the saddle point. And then one drawback to the test is that when d is 0, there is no conclusion. But this is no different from what you get in Cal 1 when you're trying to employ the second derivative test. When the second derivative is 0, there is no conclusion. So you go back to the first derivative test. So what I'm trying to point out here, just in terms of a summary, is that the test is exactly what you did in Calculus 1 with just the adjustments for the function of two variables. And we are done.